Hi, in this lecture, we will talk about the unsteady advection-diffusion transport model with finite element. In the last lectures, we considered the steady advection-diffusion reaction equation, as shown here, and we derived a finite element weak form for that, and we showed that the problem comes down to solving this linear system of equation where you have to invert a matrix of C plus K. C represents the convection, and K represents the diffusion. And F is the source term containing the boundary conditions and the known reaction term. Now, in this lecture, we will continue our analysis to the unsteady advection-diffusion equation, also considering this unsteady term. We will use a similar Dirichlet and Newman boundary conditions on portions of the boundary, but now we also have to specify an initial condition, which we need to know before we can solve the unsteady equation. So now the weak form derivation is precisely the same as before. The only addition is this unsteady terms. All the other terms are the same. So you do integration by parts on the diffusion term. So you get this term and also this corresponding Newman boundary term. And then for the unsteady term, you simply have that multiplied by the weight function. So this highlighted term here is the new term for the unsteady equation. So similar to before, we use shape functions across each element, and we discretize our domain, and we write these discretized approximations for the trail functions U and the tensor weight functions W. So we have the same element-wise matrices. We have the advection matrix, just as before. We have the diffusion matrix K, and then we have the right-hand side source term, which contains contribution from the source term, the known Newman boundary condition, and potentially the Dirichlet boundary condition could also show up in here, which we'll talk about in next lectures. And then the new matrix that we have here is the so-called mass matrix, which comes from the unsteady term. So that's essentially comes from this term here, where we have this multiplication of this same shape functions, assuming we're doing Galerkian approximation. So now what we do is that we assemble all matrices into global matrices, and this gives us a system of equation which looks, this part of the equation looks very similar to what we had before, but now we have also this mass matrix M multiplied by du dt, where U is, if you recall, U is a vector that contains the nodal unknown values across the finite element mesh. So we are now, our task is now to solve this linear system of ordinary differential equations. So we have these time derivatives here. So this is a vector U, where you have the time derivatives of U at different nodal values. So each U sub I, so U1, U2, U3, these are all of our nodal unknowns that we're trying to solve. M is the mass matrix, which we know. Then we have the advection and diffusion matrices, which we also know, multiplied by the unknown degrees of freedom. And then we have the right-hand side, known right-hand side. So here, in the steady case, we just solved a linear system of equations, just this part, but now we have an unsteady a problem. So it's a system of ODEs that we have to solve. So, and the strategy here is that, if you look at this, we've already done the discretization in space. So, our solution, U as a function of space, is discretized into these nodal values, U1, U2, so forth. And this is the vector of unknowns that we have. So our finite element weak form and discretization has taken care of the spatial aspect of the problem. But for temporal aspect, we haven't done anything for these time derivatives. And what we're going to see today is that the way that we're going to deal with that is that for time derivatives, we are going to be just using finite difference. So even though we will be using finite difference, you can also show that some of the finite difference schemes that we're going to be used to approximate the time derivatives, you can also think about that as a weak form done in time. So you can also think of the time aspect in terms of defining new weight functions that can also deal with time, but we're not going to talk about that. And it's really not necessarily that perspective. You can simply just deal with time with finite difference. Okay, now the simplest time integration scheme that you can use is a first order accurate forward Euler, where you replace du dt using this finite difference scheme. So the superscript here n denotes the time step. So the solution at time step n is shown by u superscript n, where time step n is n times delta t being your times. So if you do the forward Euler, this is what you get. Here it's your approximation for your time derivative. You have the matrix M, mass matrix M. And then on the right-hand side, you have your discretization. You have C plus K times U sub N equals F sub N. So these are all evaluated at time step N. Now, one thing that you have to be careful is that if your velocity field is also a function of time, so if your A here, our velocity vector field, is also time dependent, then this matrix C, which represents convection, will also be time dependent. So you can think about this also being evaluated at time script at a superscript n, which is the previous time step. So you have to be careful about that. You could have an unsteady advection diffusion problem with a steady velocity field, in this case where C is just constant, or you could have an unsteady advection diffusion problem with an unsteady velocity field. So in the first case, where you have an unsteady advection diffusion problem and a steady velocity field, the reason for unsteadiness could be different things. Maybe your source term, F, is time dependent. Maybe your boundary condition is time dependent, that creates the unsteadiness, or none of them. Maybe you don't even have a source term, and your Newman and Dirichlet boundary conditions are also not functions of time. However, you are interested in studying the dynamics of your advection diffusion transport once as it's reaching its steady state. In that case, F will not be time dependent, C will not be time dependent, but you will still be solving an unsteady advection diffusion. Okay, so you take this equation and then you want to solve for U superscript n plus 1 because that's your unknown time. You know the previous time step. You start from the initial condition and you march forward in time. So U superscript n plus 1 is unknown. M is a known mass matrix which you've assembled, and then this part also contains all the known parts. So M again is known, the matrices C and K are known, delta T is your time step, and UN is your previous time step solution, and Fn is the source term or the vector F, right-hand side vector F evaluated at the previous time step. So solving this is really now same as solving like an AX equal B, a linear system of equations. So what we really have to do when we're doing unsteady problem at every time step, we will need to solve a linear system of equation of this. Okay, now, well, I forgot to mention another important thing. Another reason that you might need to consider the advection diffusion equation unsteady, even though all these terms are steady, like steady velocity, steady boundary condition, is that it could help with your convergence. So if you treat it that way, it could make it easier for your finite element solver to converge rather than directly ignoring this unsteady term and directly solving it with how we did for a steady problem. So if you do it that way, when you're dealing with complex, high Peclet number transport problems, it's difficult to invert this matrix C plus K. So it will be a difficult task to directly solve this. But when you treat the problem as an unsteady problem, right, and then you just march forward in time until you reach the steady solution, which is what you want, it's much easier to now solve this system of equation. Even though you have to do more linear solves, the advantage is that you will run into you're less likely to run into stabilization problems or issues with your linear system of equation solving. Okay, now one issue with this linear system of equation that we have to solve is that we need to invert this matrix M. So this X equal B problem, we have to solve it, right? Now, since we're dealing with an unsteady problem, especially if our time step is small, which might be needed for physical accuracy reasons, especially when you have a really unsteady problem, then in those cases, it might be very difficult to solve an AX equal B linear system of equation at thousands or tens of thousands of time steps. It will be very time consuming. So one approach is that you can do is that you can make this matrix M, this mass matrix, diagonal using mass lumping. And if the matrix, which is basically one way to do it, make matrix M diagonal, is to use the row sum mass lumping method, where you just lump all the rows into a single entry sitting at the diagonal. When you do that, well, first of all, you do lose some accuracy. So you do lose some order of accuracy in your solution. However, the matrix M now becomes diagonal. And since it becomes diagonal, it's trivial to invert it. You don't really need an X equal B solver. This is now like it becomes a really an explicit scheme that you can just divide by the diagonals and find the solution by just calculating the right-hand side. Okay, now the other approach is the backward order, which is still first order, but it's more accurate or more stable compared to forward order. It will allow you to use larger time steps. So it's the same scheme for du dt, but here on the right-hand sides are all evaluated at the following time step. So this is the linear system of equations that you get. You get a matrix that's known. The right-hand side is a known vector, and you have your vector of unknowns un plus 1, the solution at the next time step that you need to solve. In this case, your matrix is much more complicated. You cannot do mass lumping like before, so you have to treat this in its full glory, basically. So, and it's more complicated also to invert this whole matrix. So the AX equal B solves will be more time consuming, but of course the advantage here is that you can probably take much longer times. I should also mention that sometimes you do not want necessarily to take a larger time step. That's not always good, because sometimes for physical accuracy reasons, we need or we're interested in having time steps that are small. So if because of accuracy, if your problem is like just by nature highly unsteady, or you have physical instability in your problem you want to capture, so you want to use a very small time step to capture those physics, then you probably want to use a method like forward order as opposed to backward. Okay, finally, we can also use second order methods. The Crank-Nicolson method is a second order accurate method. So here, the left-hand side, the time derivative is again the same, but everything else, we just average it for different time steps. Okay, so there are 2 time steps. And then this is what you get at the end. You have a more complicated right-hand side. Again, you have a difficult matrix to invert, but it looks very similar to the backward Euler matrix if you compare these two. So you still have to invert this matrix or really solve this AX equal B problem at every time step. Now, finally, based on my experience, this Crank-Nicolson method if you're dealing with very high picture number mass transfer problems that are difficult, you have like sharp interfaces in your concentration or temperature fields, and you're dealing with challenging transport problems and that are highly unsteady, this might not work very well, and you might see stability problems by using Crank-Nicolson. So in those scenarios that you have highly unsteady and difficult problems, the best choice that you can use for implementing your time integration is the generalized alpha method. So here I've included 2 references for the generalized alpha method. The first reference talks about the generalized alpha method in the context of Navier-Stokes equation, and the second method talks about it in the context of structural dynamics and elastodynamics problems. So I will put a link to these 2 references, great papers, that if you're interested in the generalized alpha method and learning about that method for time integration, you can check out those papers.